Good afternoon. Howdy all, and welcome back to the channel. I'm Professor Parks, and this is yet another of my lectures on the solar system, where I talk about the solar system on an introductory, but hopefully a little bit more in-depth than I have done in previous lectures. Hi, George. Well, before we get into that, one of the things that I would like to do is to, well, first I want to answer Judy's question. Where is it? There it is. Judy asks, if I make an updated observatory video, can I show more of the main telescope, especially the mountain controls? Yes, that is definitely something I want to highlight. The observatory video, which is on my channel, was a live stream, and unfortunately I did not realize that, hey, if you go into a large metal dome, your internet, your Wi-Fi don't work. So unfortunately it cut out whenever I was trying to get into the dome, and so I wasn't able to get good views of the telescope and its accoutrement. And considering, kind of following up on a question you had previously asked, if have things changed around here, and the answer to that question is yes. With regards to the 32-inch telescope, we have added a infrared camera, a dedicated infrared camera with a cooling system, a water cool. Well, I need to actually. It's not water cooled. It's some other chemical, but essentially it's a liquid cooled IR camera. And so yes, one of my aims is to redo that introductory video, not as a live stream, but as something that's a little bit more polished, a little bit more put together. Unfortunately, that's going to require time. It's one of the reasons why I do not really do any edited videos anymore, is because I just don't have the time to do it. But it is coming. The second thing I would like to share is more of a general public or channel announcement, is that I'm going to resurrect Coffee and Science from the Dead. It probably will not be as really an interview show as I had originally intended. I do plan on getting additional guests, astronomers, scientists around the friends of mine in the community, but I also want to use it as a way to talk about some of the issues or open questions in astronomy, or if someone has someone in the audience or a viewer knows of an open question in physics or any other science, please feel free to let me know, and hopefully we can, maybe something we can work it out. But so Coffee and Science, I had him on Sundays at 10 a.m. Eastern time. So right now that would correspond to, I believe, 3 p.m. UTC. And the subject du jour is, or the subject matter is basically this. So it's been pointed out to me by a certain individual that there are anomalies, or at least he claims that there are anomalies in astronomical redshifts. And apparently he has nine instances of these anomalies. And so what I'd like to do is I'd like on Sunday to address these issues and to see whether or not these anomalies are actual problems. If they are not, then I can explain why they are not problems. But if they are problems, I can acknowledge them and let folks know what it is that astronomers are doing to rectify that problem or to try to solve that problem. So that's going to be Coffee and Science on this coming Sunday at 10 a.m. So hopefully my scheduling will work out. A fair notice, they are finally actually working on my building because apparently there's a problem with the ledges. Long story, really mundane and boring. All I will say is that occasionally you might hear jackhammering or kind of a low vibrating sound. Hopefully, I think they're kind of done, but hopefully that is not going to interrupt us too much. So anyway, yeah, so where were we before? I believe we were here, and I want to just recap what I talked about in the last lecture, which was essentially the beginnings of the Copernican revolution, the movement from a heliocentric model, a geocentric mathematical model of how the stars, how the planets move around the sky, to a heliocentric one, first made by Copernicus and then basically redone by Kepler. And Kepler, when he created his model, as it were, really what he did was he formulated three laws of planetary motion. The first was he got rid of the Aristotelian belief that planets, or really objects, move in perfect circles. In actual fact, if we're talking about bound orbits, then these orbits are actually elliptical. Later on, I will talk about the difference between a bound orbit and an unbound orbit. It might seem a little bit, unbound orbits, even to me, seem a bit counterintuitive, but we'll get into that later. But so for planets specifically, what he stated was that a planet will go around the sun in an ellipse. It may be a circle, but but from an observational evidence point of view, it's definitely ellipses. The second law is equal areas and equal times. This refuted the Aristotelian belief that things move in uniform motion, that the speeds and velocities of planets are constant throughout its orbit. As we find, or as Kepler found through Tycho's observations, planets that are closer to the sun move faster than planets that are closer to the sun, near perihelion, move faster than planets that are further away from the sun at aphelion. And then finally, Kepler's third law, or his harmonic law, which I was talking about the fact that it's commonly represented as the period of a planet squared is equal to its semi-major axis cube. And that is true, assuming that you have the appropriate units tacked on, period in years, semi-major axis in AU. In actual fact, and I know this is probably difficult to see, Kepler's formulation actually was a ratio where he stated that the period of the planet with respect to the period of the Earth squared is equal to the semi-major axis of the planet to the semi-major axis of the Earth cubed. So what that ultimately means is that Kepler's third law was limited to the solar system. Really, it was only applicable to planets orbiting around the sun. It also, as we'll find, hid some very, very interesting physics. This is what we refer to as an empirical law. It is a law which is found through the study, or basically the fitting of data. It is not I honestly don't know, maybe Clive knows, what the opposite of empirical is. I guess I hate to use the word theoretical, but foundational, basically a law that is derived from first principles, or basic physical principles, rather than observed data. And so this empirical law, unfortunately, misses out on a lot of cool physics surrounding it. But let me just wrap up with the Copernican revolution before we get into what physics Kepler's third law leaves out or misses. And really, the ending of the Copernican revolution was due to a dude named Galileo. Galileo Galilei was an Italian physicist. Cool dude. He's number 3 on my dead astronomers I'd like to get drunk with. If you want to know number 2, that would be Fritz Zwicky. Check him out. Really awesome dude. Anyway, Galileo has been known, there may be a misconception out there that Galileo invented the telescope. And the telescope that he used is very much like this one. I don't remember if this is a mock-up or if this is actually one of the telescopes that Galileo had built and used. Galileo did not invent the telescope. He was simply the first person on record to use a telescope to look at celestial objects. The person who invented the telescope was probably Hans Lippershey in 1602. But the story of Galileo and the telescope is actually kind of an interesting tale in the sense of if you're an astronomer, if you're in science, one of the things that you know and really kind of it's sort of it's a dirty little secret is that there is a very strong connection between science and the military. And this is one of the first examples I've ever seen of this sort of interchange, is that Galileo went to the leader of Florence, the Duke, I guess, and he said, "Hey, I need some money because I want to build one of these things, and they ain't cheap." So the Duke was like, "All right, well, what does it do for me? You know, you want to look at the sky, but what does this do for me?" And Galileo told him, "Well, it magnifies things at a distance. So you can use this telescope, if you allow me to build it, to see armies approaching much sooner than you would with your naked eye." And the Duke was like, "Hey, you know what? I could use that." And so he gave the money to Galileo, and the rest is history. So what did Galileo use this for? What were the observations that Galileo is most famous for in terms of his use of the telescope? In no particular order, these are all about the same time, 1609, 1610, somewhere in there. We'll start off with the moon. He looked at the moon, and when you look at the moon, naked eye, really the only features you can see are the mare, or the seas, as it is in Latin. Those are the dark gray stains on the surface. Those are actually ancient lava fields, but you really can't make out anything else. And so you might have the impression that the surface of the moon is rather boring, that, you know, in fact, it has its dark gray stains and the rest of it is really unremarkable. What Galileo showed was that no, there was actually quite sophisticated sort of topography on the moon, and that the moon had in fact mountains that had craters, and he used shadows. He used geometry and shadows to work out what the heights and depths of those craters were. And he demonstrated that some of these mountains on the moon were kilometers in height, 1, 2, 3, all the way up to around 4 kilometers in height. So as high or even higher as mountains here on the Earth. And that was something that was fairly revolutionary, because again, if we go back to the Aristotelian belief, Aristotle thought that all surfaces in the universe, and then later picked up by the church, all celestial bodies are perfect. They're perfect spheres, they're unblemished, yada, yada. And so what Galileo showed was, no, actually the moon is quite blemished. It has definitive topography that can only be explained as surface features. He found new moons, which again flew in the face of the idea that the Earth was primary, that all things in the heavens would revolve around the Earth. As a matter of fact, he found what are now known as the Galilean moons, Io, Europa, Ganymede, and Callisto. These are 4 bright moons that, if you have even a set of good binoculars, you can see them. They appear as basically 4 dots, or they appear as dots right by Jupiter in a nice plane. Basically, we see them pretty much just flat on. And if you look at them even over the course of hours, because I've seen this, the inner moons, Io and Europa, you can literally notice that they move with respect to Jupiter. The outer planet, or the outer moons, not so much. Their periods are a little longer. But with Galileo, he made observations and records of the positions of the moons over the course of months. And he noticed that they changed regularly. They swung backwards and forwards. The only explanation to really explain that, or at least the best explanation he came up with, was that these dots were not in fact stars. They were in fact solid bodies that are orbiting around Jupiter. Again, you can use geometry to demonstrate how you would see that from an edge-on perspective. So again, Aristotle is wrong in that the Earth is not primary, in that there are bodies orbiting around other objects. I mentioned this last time. Galileo saw the phases of Venus, which cannot be properly represented using the Ptolemaic system in any way whatsoever. Depending on how you finagle the Ptolemaic system, it either cannot show phases, you would not be able to see phases of Venus, or the phases would be wrong. And the reason for that is, again, the geometry between the Sun, the Earth, and Venus. Based on where these objects are relative to each other, our ability to see the lit portion of Venus changes over time. Now, Galileo, I think on my, I usually give a quote by Einstein in the very first lectures of mine, or Einstein basically says that Galileo was the father of modern physics and maybe even modern science. And the reason for this is that Galileo was the first on record to create experiments without really an overarching worldview, as it were. And I'm probably going to get this backwards, but Aristotle was a deductive thinker in that he had a larger worldview, and then basically his thought process went down to get down to individual, to explain individual motions, like the motion of an arrow flying through space, was very dependent on his overarching worldview. Galileo was inductive. He basically said, no. Let's get rid of a worldview. Let's get rid of any kind of bias or any kind of bias, and let's look at individual phenomena and see if we can find commonalities that can then be brought to be made into a worldview. And so he made observations. The ones that I'm most familiar with are the inclined plane problem and the pendulum problem. And he was able to, through controlled experimentation, show that, for one thing, that mass, that things fall, the rate at which something falls is, to first principle, irrespective of its mass, assuming we neglect air resistance and all that. He also demonstrated, he was actually the first to demonstrate or to posit that the motion of bodies are relative. So there is a thing called Galilean relativity, which is similar to Einsteinian or relativistic relativity. The main difference is that Galileo did believe that there was an absolute frame of reference from which you can measure things, and he didn't believe, or he didn't. He just said that velocities were additive. So, for example, an example of Galilean relativity is if I'm on a truck, I'm sitting in the bed of a truck, and I'm moving at 88 miles per hour going forward, and I don't go into the future or go into the past. If I throw a ball forward at 10 miles an hour, then if I were to measure that ball, I would measure 10 miles an hour. If someone were to measure it from the ground, if someone were to basically watch me do this from the side of the ground, they would actually measure the ball moving at 98 miles per hour. And so basically the idea with Galilean relativity is that velocities are simply additive. Howdy, Chris. Welcome. Actually, kind of an aside. One of the things here, that we're doing, that photo, the student organization is doing, is that we just picked up a kit or supplies from a gentleman who donated. Basically, he was in the process of grinding his own mirror to build his own telescope. He didn't finish it, so the students here are going to finish that process of grinding out that mirror and actually build a small Dobsonian telescope. And yes, the process by which you do that is intensive, and I highly respect those who do that by hand. But anyway, so Galileo basically was the one who really didn't codify the scientific method, but he definitely followed the scientific method. You can see that method within his within his experimentation. And he was really the one who started codifying the beginnings of classical mechanics. So before we get into classical mechanics, before we start getting into the thing about Einstein and Newton, or excuse me, Newton and all that kind of good stuff, let's define a few terms, or get a few terms straight. There are these things called scalars, and there are these things called vectors. A scalar, simply put, is a quantity that has an amount, a size, or in physics parlance, it has a magnitude. So speed, for example, is a scalar. If I tell you that I'm going 88 miles per hour, then you know that my speed, the magnitude of how fast I am going is 88 miles per hour. And that's all you know. You don't know where I'm going. You just know that's the rate at which I'm traveling. As opposed to a vector has both magnitude or size, as it were, or amount, and also a direction to it. So if I say that I'm going 88 miles per hour due north, that is a velocity. That I now know the magnitude or the size of the thing, and I now know the direction of the thing. So that becomes important when we start talking about changes in things. So let's move on a little bit and talk about acceleration. Acceleration is defined as the change of an object's velocity over time. Acceleration is also a vector. It has a magnitude and it has a direction. So when I say that acceleration is a change in the object's velocity over time, that actually can happen, or that can actually happen one of two ways. Something can accelerate if the object's speed changes, basically the magnitude of the velocity changes. So if I go from 88 miles per hour to 0, then I am decelerating or accelerating in the opposite direction of motion quite a bit. Or if I go 88 miles per hour and I take a left, but my speed is still 88 miles per hour as I go into that curve, I have also accelerated, because now, instead of changing the magnitude of my speed, I have changed the direction. And so that's going to be a critical point to know when we talk about orbits. Mass can be defined a whole lot of ways. The definition that I'm going to be using from moving forward is that mass is simply a measure of the stuff of an object. How much matter an object is comprised of. That's it. That's my definition of mass. There are others that I'm sure are equally beautiful and nice, but this is the one I'm taking to prom. Is mass is the amount of stuff in an object. Force. I'm going to go over this a little bit more mathematically, or a little bit more specifically, but for now, just say that a force is a push or pull on an object that, if unbalanced, meaning that there is more of a force going in one direction than in another, then it can change the object's motion. Oh, hi, Gary. Heaven is above, earth is beneath. That establishes up and down. Everything in between will move in its equilibrium if unrestrained. Wow. Okay. So basically, what you're saying here is you agree with Aristotle. Assuming, I think that's almost specifically what Aristotle would go with. We now know that that's no longer the case. Up and down basically are subjective measures, and hopefully I can illustrate that as we move forward. Let's see. So I've already talked about an example of speed. An example of acceleration is, so say I have an object that is falling at 9.8 meters per second squared. What that means is if I let go of that object and it begins to accelerate at that amount, in 1 second, its velocity is going to be 8, or So it's accelerating at 9.8 meters per second squared. After 1 second, that object will be traveling with a velocity of 9.8 meters per second. If left by itself, it will continue to drop, and the next second it will have, let me see if I can do the math, a velocity of 19.6 meters per second, and then going further and further down. So that's the idea of an acceleration, is that it's the rate of change of a velocity. As I mentioned before, Galileo illustrated through his experiments, like I said, both the inclined plane and the pendulum, that the acceleration of an object, the downward acceleration of an object, is irrespective of mass. It is 9.8 meters per second squared, approximately, and regardless of the mass of the object. It could be a semi-truck or it could be a feather. A great example of this is, I believe it was the Apollo, I always get this wrong, it's either Apollo 15 or 17. The mission specialist, or the mission commander for that, has a feather and a hammer, and because he is on the moon and the atmosphere is almost non-existent, he was able to drop them, and both of them dropped at the exact same rate. You can't do that here. You really can't see that here unless you do unless you really have a thoughtful experiment, because air resistance is a thing. But ultimately, it doesn't matter what the mass of an object is. I keep touching my nose. It doesn't matter what the mass of the object is. They're all going to accelerate at 9.8 meters per second squared, approximately, when you are near the Earth's surface. Pretty much just said that slide is basically what I was just saying. So let's go into Newtonian physics, or classical mechanics. Newton was a weird dude. Newton's number 4 on my. He's not an astronomer, but he's number 4 on my list of astronomers I'd like to get drunk with, or at least the Newton before he got mercury poisoning and went nuts. But anyway, Newton's an interesting dude. He was obviously, he is essentially the father of classical mechanics. He was the first to really formulate a working theory of gravity. He was very big into optics. One of my favorite stories about Newton is that he was curious to see whether or not the bending or the refracting of light that he saw through a prism would change if you actually change the shape of the prism. Now, the prism itself obviously is glass, and so changing its shape would be very difficult because it's so rigid. So he said, aha, I know of a possibly squishy lens, my eyeball. So he stuck a pin, supposedly, anecdotally, he stuck a pin in his eye and moved it around to see whether or not, to see what he could see. So I don't know if it's true, but it sounds cool, so I'm going to say that it's true. But that's the kind of guy from all accounts that Newton was. And so what I'm going to be talking about here is primarily his 3 laws of motion and his law of gravity. These laws are, because of the Copernican principle, these laws are universal. They apply to, if we are not going to quibble about quantum mechanics, there are limitations. So if you get to some atomic particles, things get a little bit weird. But if you're talking about everyday terrestrial occurrences, classical mechanics works great. It doesn't matter what you're talking about. You're talking about cells, you're talking about apples, you're talking about stars, orbits. Classical mechanics works very, very well. One of the tricks, and again, this is kind of going back to the philosophy of science. One of the ways that you can understand that what you come up with is true, or probably, or correct in a way, is that Newton was thinking about gravity, and I'm probably getting ahead of myself, but he was thinking about gravity. He has this nice law to explain motions, and he said, how can I really convince myself that this is real? All right, well, Kepler was kind enough to come up with these empirical laws based on what he saw directly from observations. So and if I believe that gravity is the mechanism by which planets move around the sun, then what I should be able to do is I should be able to take my theory of gravity, my law of gravity, and I should be able to derive or basically arrive at the same laws from my theory that Kepler was able to arrive at from data. And if I can do that, if I can show that, then that adds a lot of credence to why my idea of gravity is correct. But first, let's talk about his laws of motion. Let's talk about the first one, otherwise known as the inertial law. Newton's first law states that an object in motion will stay in motion, and an object at rest will stay at rest unless acted upon by an unbalanced force. So if you have an object sitting in space, that object is going to sit in space for eternity unless a force is applied to that object, which will then cause it to move. Aristotle, all on board with that. Basically, Aristotle believed, as Gary pointed out, that all things have an equilibrium position. Once they reach equilibrium, they stop. They basically don't move unless you move them out of equilibrium. The problem that the next thing is where Newton goes further than Aristotle. Whereas Aristotle will say, basically, like I said that everything will come down to an equilibrium, will slow and come to a stop naturally. Newton says, no. If you have an object moving through free space, it's going to move at a constant velocity. So the size, the magnitude of its motion, and its direction, both of those two things are going to remain unchanged for eternity unless a force comes by and interacts with it. And it's going to do one of two things. It's either going to change the speed, the magnitude, or it's going to change the direction, or both. So I guess three things. The reason why we don't really see that, or why that seems counterintuitive on the Earth, is because of resistance forces, friction, air resistance, that sort of thing. But those are forces. Those are the reasons that why, if I slide this pen across my desk, it stops. Because of the frictional force, the force that is opposing the motion, is causing that velocity to change. It's causing it to come to rest. Those of you who are around ice, this becomes a little bit more intuitive, in that if you were to try to slide a rock across the ground, it's not going to slide very far. But if you put that same rock on ice, then it's going to slide a whole lot faster or further away. Hey, Nimrod, what is Shaman? Slamin? I haven't seen you around, so howdy to the channel. Whoops, that's not what I wanted to show you. What is the formula for buoyancy? I don't know if you were asking that of me or of Gary, but unfortunately, I will not be getting into buoyancy because that is more physics than it is astronomy. But buoyancy is a function, essentially, of gravity. So that's the first law. An object in motion will stay in motion, or an object in motion will stay in motion unless acted upon by an outside force. An object at rest will stay at rest unless acted upon by an outside force. Now, the second law, otherwise known as the force law. Now, there are different. I can think of two different formulations for it. The most famous of which is F equals ma. Now, I want folks to take a second and really try to conceptualize this, because to me it's amazingly powerful. Newton's second law of motion basically can be used to describe all motion, or at least all motion that we see. It is everywhere. Anything that, you're talking about, birds flying through the sky, me throwing things across my desk, whatever, the Newton's second law of motion is in there somewhere. And it's simply F equals ma. To me, that is utterly profound. That such a powerful concept of force is related in such a simple way. Just force is equal to the mass of an object times the acceleration that that object experiences when that force is applied. It just, to me, is beautiful. It's profound. Like so. Anyway, I'm getting ahead of myself. So what is F equals ma? Simply put, really, you can think of it as the consequence of, in this slide, a rocket carrying a small car or a rocket carrying an asteroid. If you apply an equal force, if that rocket is applying an equal force in thrust, then the rocket carrying the small car is going to accelerate faster because its mass is smaller. And a rock carrying an asteroid, that overall system has a larger mass. So therefore, if you apply the same thrust or the same force, that mass is going to experience a smaller force or a smaller acceleration. There's another way to look at it. And this is the way I think is a better visualization to me, is I often ask my class, would you rather get hit by a bicycle going 5 miles an hour or a semi-truck going 5 miles an hour? And usually people, unless they're really masochistic, choose the bicycle. And the reason for that, even if they're not aware of it, is mass. They may not call it mass, they may call it weight, they may call it size, whatever. The reason behind it is that a bicycle weighs less, has less mass. So if the two objects are accelerating towards you, I really should have said accelerating at you at 5 miles per hour. If they're experiencing the same acceleration at you, then you once you get hit, are going to experience a different amount of force from a bicycle as you were from a semi-truck because of the mass difference. And so this is the equation that I'm going to use, which is F equals ma, as I said. And then you can rewrite that A, the acceleration of a body, is equal to the force acting divided by the mass of that body. Yep, Nimrod, I guess you may be. This becomes important when we start talking about things like why is it that the moon appears to move whereas the Earth doesn't, if they are experiencing the same force. I guess with this, what I can say is going back to vectors. Changing motion, again, is both, you can think of the velocity, again, is a magnitude and direction. If you apply a force in the opposite direction, then you're going to, the opposite direction of that velocity, then you are going to apply an acceleration that is opposite to that velocity. And so those two vectors are going to essentially compete against one another, and depending on which one is larger, in a way, the object is going to either just slow down or it's going to actually reverse direction entirely, slow down and reverse direction entirely. Although I suppose, really, depending on how much you apply, that would actually be the case either way. But what I'm trying to say is that, again, when we talk about these things, we want to keep in mind there is a directionality to it. And force is a vector, acceleration is a vector, force is a vector. So force has both magnitude and direction. And then we have Newton's third law, the reaction law. which is commonly said that for every force, for every action, there is an equal and opposite reaction. If you apply a force to something, then Newton tells us that that something then applies a force directly on you, but in the opposite direction. Now, really think about the action of walking. How do we walk? How do we propel ourselves forward? You might say you push off on the earth, but what does that really mean? What that means is when I apply my foot to the ground, I push on it. What that means is that the ground is going to push back at me with an equal and opposite force. That is what causes me to be propelled forward. Coincidentally, or not coincidentally, but incidentally, I am also causing the earth to accelerate. So anytime I walk forward, I am exerting a force on the earth is exerting a force on me. Because my mass is so insignificantly small in comparison to the force of the earth, I get accelerated forward, whereas the earth basically just shrugs its shoulders and goes on with its day. But if we were to get rid of all other forces acting on the earth, and you were just to have me standing on the earth and I walked forward, then the earth itself would accelerate at a very, very small way, very, very small magnitude in the exact opposite direction. So that's how we move forward. If we did not have Newton's third law, if Newton's third law rather was incorrect, then we wouldn't be able to move because we'd have no way of actually propelling ourselves forward. This also explains why an astronaut in space, if you see them in movies, they're always flailing around, is because they don't have anything to push off of. There is no medium upon which to push off of. They have to either find something to push off of, or they actually have to throw something. And if they throw something, then they are applying force to that something, a wrench or whatever, and then that wrench is applying a force back. And so causes the astronaut to move. That's what I think about it. So that's the reaction. So what does all this have to do with gravity? Well, rather, what is gravity? Now, I have a video out there, and I think it's entitled something like "Gravity is not a force; it just isn't." What I will say, the caveat that I will say now, is that I am going to be discussing gravity in the context of classical mechanics. Classical mechanics is an entirely valid, a perfectly valid explanation or description of the universe when you were talking about massive objects moving slowly or in the presence of a relatively small gravitational field. If relativity is not a big factor, classical mechanics is a perfectly valid way to describe things. If quantum mechanics is not a factor, again, classical mechanics, good stuff. So in a classical mechanics sense, we are going to state that gravity is a force. Just as a caveat. So if you ever look at YouTube videos and you see YouTube videos, including mine, that say gravity is not a force, investigate why they are saying that. But here I would want to just say that from a classical mechanics standpoint, we're going to treat gravity as a force. Specifically, gravity is a force of attraction between two masses separated by some distance. Written out, we have that the force of gravity in all of its glory is equal to a gravitational constant, which is just a numerical constant, times the mass of one object, times the mass of the second object, divided by the distance between them, squared. And when I say the distance between them, what I really mean is the center of masses of each body. So if you have two spheres, for example, the distance is the distance from the center of one sphere to the center of the second sphere. That is the distance I'm talking about, not the surfaces of the two. Gravity is what we call an inverse square law. The inverse square law pops up a lot. pops up pretty much, well, it pops up a lot. It pops up with gravity, it pops up with electrostatics, it pops up with brightness. Nature just seems to like the idea of an inverse square law. What this means is that if you take two masses and you separate them by a factor of 2, so you double the distance, the amount of gravity that each individual mass experiences goes down by a factor of 4. If you triple that distance, gravity goes down by a factor of a 9th. So forth, so on, and so forth. If you take the two masses, contrary to this, if you take the two masses and you have one of them, you basically just cut the thing in half and throw the other half away, then the gravity decreases by a factor of 2. It halves as well. So if the distance gets doubled, force goes down by a 4th, mass gets halved, force goes down by a factor of 2, or is cut in half. So what about the applications of this? I really wish I had a whiteboard that I could access easily. But let's look at, so Galileo told us that all masses accelerate at roughly 9.8 meters per second near the surface of the Earth. How do we know that that's gravity? How do we know that it's gravity that is causing it? Well, the 9.8 meters per second squared was a measured quantity. Galileo measured that value through his experiments. And again, as I was saying before, if you can have a theory and you can essentially derive or predict that same value, given the assumption that the core principle is what's acting, so the reason why things accelerate at 9.8 meters per second is because of gravity. If you can use your formulation of gravity to predict that, that's what masses should do, what they should accelerate for, then again, real confidence in that your idea of gravity is correct. Now, the way to do this, and again, this is where I wanted to have a whiteboard, is let's take Newton's second law, F equals ma. So the force applied to a mass is going to result in an acceleration. So let's say that force is gravity. The apple is falling from the tree because gravity is the force acting upon it. We know that Newton knows, or Newton put forward, that the law of gravity, or that gravity should behave as a constant g times the mass of one object, the mass of the second object, divided by the distance between them squared. So in this case, the mass of one object is the mass of the apple, and the mass of the second object is the mass of the Earth. So what we can do is you have ma on one side, and that's equal to g m of the apple, m of the apple times the acceleration on that apple is equal to g times the mass of that apple times the mass of the Earth divided by the radius of the Earth squared. What you immediately find out is that the mass of the apple is on both sides of the equation. So they cancel each other out. They go away. So immediately we can see that gravity is accurately shows what Galileo found empirically, that the acceleration of an object under the influence or the acceleration of an object as it is falling is independent of mass. So it doesn't matter what the mass of the object is, its acceleration is going to be the same as it falls. So Newton immediately right off the bat shows you that. So what about this 9.8 business? Well, simply put, if you just put in the numbers for g, you put in the numbers for mass of the Earth, you put in the numbers for the radius of the Earth, and you square it, then you get a number that is 9.8 meters per second. If you want to get precise about it, and you're thinking to yourself, well, the acceleration due to gravity actually changes with height, well then great. You are onto something, in the sense that r, while I have notated as the radius of the Earth, In reality, again, that r is the distance from the center of the Earth to the center of the apple in this case. So really, you have to take that distance into account when the object is falling. But since the additional, I mean, assuming the tree is only maybe a meter high or 5 meters high, that's peanuts in relation to the size of the Earth. So really, it's going to be 9.8137, blah, 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 blah. It's going to be a whole bunch of numbers in the back, which really most people won't even need or use. But if you get up to like Everest or Mauna Kea, which is like 14,000 feet, you can convert that into miles or kilometers in your leisure, that is a more significant height. And so what we find on average is that if you're at sea level, then the acceleration due to gravity is around 9.81 meters per second squared. If you're on the top of a mountain like Mauna Kea, then it's measured to be 9.80 meters per second squared. It's slightly smaller. Things fall at a slightly smaller rate as if you are away from the Earth, further away from the Earth than if you're really close to it. So if you want to lose weight, real easy trick. Just go up and you'll lose weight. Technically. So how does this apply to orbits? As I said before, this is the title of this lecture is Gravity in Orbits. How does this apply to orbits? Well, what Kepler posited was that there is a force that exists. I don't think he called it a force, but he called it something akin to a force. There is something that's compelling the object to be accelerated towards the center of towards the sun. It's keeping it in its orbit. And this is what we refer to as a central force, more specifically, centripetal. A central force which gives rise to a centripetal acceleration. So let's take the thing that I've been bashing, uniform circular motion. It's like a car that's going around in a circle. Its speed doesn't change, so that's the uniform part of it. It has a certain velocity. So time one, the velocity. So let's say it's traveling at 88 miles per hour. Its velocity is pointed in that direction, so it's going up like this. In order for it to continue around that curve, there has to be a pull, an inward pull, in order to change that velocity vector, that direction of the velocity, down to where you see it in time two. A better way of illustrating this, I think, is you take a ball on a string, you whiz it around your head. You whiz it around your head, the ball is going to basically orbit your head. It's going to spin around above your head in a circular pattern. And then let go of the string. Once you let go of the string, the tension, which is causing the ball to accelerate inward, or basically keeping it on its track, as soon as that tension is gone, as soon as that central force is gone, Newton's first law takes over. That ball is going to move in a constant velocity. It's going to continue to move at the same direction, the same speed that it had at the very instant that tension went away. So it flies off in basically a tangent direction. And so that's a central force. So gravity is a central force. And this helps explain weightlessness, or the concept of weightlessness. Let me first define what weight is. What we call weight is a force. We often will conflate that with mass. That's a problem, in that the two are not the same. Your mass and your weight are not the same thing. Mass, as I've defined it before, is the amount of stuff that is in an object, or your mass is the amount of stuff in you. Your weight, and that mass is independent of your location. Your mass is your mass here. Your mass is your mass on the moon. Your mass is your mass in Andromeda. It doesn't change unless you start cutting off body parts or start eating a whole bunch of food. Your mass is not going to change. Your weight will, depending on location, because your weight is your mass times the acceleration of the local gravitational field or the local gravitational force that is applied to you. So you feel weight because gravity is pulling your mass downward. And really, when you think of you feel weight, that's because the ground is there and it's pushing up on you. Again, Newton's third law, you're pushing down on the ground because gravity is forcing you into the ground, and the ground is then pushing up on you. That's what it means to feel weight. Here, the weight, to let folks know, last time I weighed myself, I was, 120 kilos, 120 kilos, I think. I want to get down to 100, not that anyone asked, but I'm 120 kilos here. If I were to go to the moon, I would weigh 1/6 of that. So I would weigh 20 kilos on the moon. So if you really want to feel good about yourself in terms of your weight, go to the moon. You will feel way better about how you feel because you will feel 1/6 of what you do here. Now, what about weightlessness? What about the idea of astronauts in the ISS, floating around? Whee! Do they have no weight? Yes, in a way. What it does not mean at all, is that the astronaut isn't being accelerated, that gravity no longer exists. Gravity always exists. Gravity is always there. The best example I can give you for weightlessness is imagine you jumping off a cliff. When you jump off a cliff, again, ignore air resistance. If you're jumping off a cliff, and you can feel it, even with the air resistance, you can feel it. You feel weird. You feel as if there is a weight kind of lifted off you. Your stomach seems to come up into your body because, again, it's no longer being pushed down because of gravity. It's just going to kind of float. That, a person that's falling or in free fall, is also technically weightless. What they are experiencing is how can I put this? I know I'm going to get this analogy. So an astronaut on the ISS is essentially in free fall. They are falling towards the Earth, but are constantly missing. They're constantly missing the Earth. And that's because they are in a circular orbit. They are in an orbit because of that. The ground is pushing up on you. That's the dumbest thing I've ever heard. Okay. Don't know how to take that, but Gary, if you would like to stick around after I am done with this lecture, I would love to have a conversation with you and try to dissect why you think that's the dumbest thing you've ever heard. Personally, the dumbest thing that I've heard lately is that pi cannot be used to calculate the area or volume of anything. So because it's a transcendental number. Whatever. All right. Anyway, getting on with this. So let's talk about orbital motion. I'm going to end this with talking about orbital motion. I know this is going a bit long. So when we think about orbital motion, again, we're going to kind of ignore air resistance. You can add air resistance, but it just makes things a little bit more complicated. The basic principle is still the same. Let's take a cannon that's high up on a mountain, and you fire it off with a certain amount of gunpowder. Basically, the gunpowder is going to dictate how much force you apply to that cannonball. You set the cannonball off, you fire it. The cannonball is going to now go straight out and fly out into space. Now, at this point, once the cannon has fired, the only force acting, again, we're neglecting air resistance, the only force acting on that ball is gravity. So it has no acceleration in the x direction, the direction that it's traveling. Only has acceleration down. This is what causes a projectile to fall to the ground or go through what is known as a ballistic trajectory. So it falls to the ground. Easy peasy. See this all the time. But let's imagine you... Oh, I know who Gary is. Well, anyway. Let's say in this thought experiment, you add more gunpowder, which I always like. Add more gunpowder, you add more force, the thing fires off. Now the object is propelled outward with a larger initial velocity. So it's going forward faster. Gravity is still the same magnitude. It's still going to accelerate downward at the same rate as it did before. But this time, so it's going to take the same amount of time to fall to the earth. But because it has such a larger velocity going forward, it's going to get further along. So it's going to go, instead of going, say, a mile, it's going to go 10 miles. If you keep going with this thought experiment, you're going to eventually, if you keep adding gunpowder, you keep making the force larger, and you keep making the initial velocity larger, you're going to get to a point where the rate of fall, essentially, exceeds the amount of time it takes to go around the Earth. You have now achieved that velocity that velocity that the ball has initially is what we refer to as circular velocity. Once you've got that velocity, you are now in orbit, in what you would conventionally refer to as an orbit, going around in a circle, and you keep going that way until you are acted upon by until you are acted upon by an outside force. Not quite analogous, but if the only force acting on you is gravity, you're just going to keep going around and around and around. If you increase the velocity of the ball, if you keep doing this, if you increase the velocity of the ball, now, instead of a circle going around, you're actually going to go around in an ellipse. Please tell me I have this. No, I don't. I have a better graphic than this. But so the first orbit is a circular orbit. You go around like this, basically the circle. If you add more velocity, you add more energy to the orbit, you now have an ellipse. So perigee would be where the cannon fired you off at. You would then move to an apogee position, which is further away from the Earth, and then so forth. You keep adding, if you keep adding the gunpowder, the ellipse is going to get more and more eccentric, to the point that if you add enough gunpowder, you add enough power to it, you're going to hit what is known as this escape velocity. The escape velocity is where you have essentially overcome the gravitational force that will bring you back to your original starting position. So you have escaped. Gravity is still there. Gravity is still acting on you, but you have enough velocity to get out of town, to get out of Dodge. For the Earth, that is 11.7 kilometers per second, or Mach 24 if memory serves. Artemis and any astronaut the astronauts on Apollo, the astronauts on Artemis, they're going to have to reach that speed in order to get to the moon, to escape the Earth so that they can get to the moon. Well, that's probably an inaccurate statement. If they were to, I don't know. I'd have to revisit that. I apologize. I'm thinking to myself that in order to get to the moon, you may not have to be moving that fast. But in order to escape the Earth entirely, if you want to go out to Mars, for example, you have to reach that speed. That puts you in what we refer to as a parabolic orbit. Now, here is where it gets a little bit counterintuitive. A circular orbit and an elliptical orbit are what we refer to as bound. The object goes around the satellite goes around the host body indefinitely. So the moon is in a bound orbit. It goes around the Earth indefinitely. It's just going to keep going around the Earth unless something comes around and bumps it out of the way. That is what we call a bound orbit. A parabolic orbit, and again, continuing with this analogy, if you keep pumping gunpowder into this and you fire it off with even faster or a larger velocity, you're going to get into instead of a parabolic orbit, you're going to get into a hyperbolic orbit. Hyperbolic orbits and parabolic orbits are still technically orbits, but they are unbound, meaning that the object in question is not going to return to its starting location. So something that has an escape velocity, as I said, is going to escape Earth. It's going to travel in a parabolic orbit, and it's going to go off into space. If you switch that around and you have something that's going in a parabolic orbit that's coming at the Earth, it's going to come to the Earth, it's going to swing by the Earth, and it's going to go out, and it's going to fly out into space. If you ever wondered why we know that the comet Oumuamua, Oumuamua, you can Google it, why we knew that that was an interstellar comet is because we mapped its trajectory and it was hyperbolic, which means that it was unbound, which means that the comet could not have originated within our own solar system. So those are the four, hey Gina, those are the four types of orbits. You have a circular orbit, which is the lowest energy orbit. You have an elliptical orbit. You have a parabolic orbit where the object, and those first two are bound. And then you have a parabolic orbit where the object essentially will not come back around to the object that's gravitationally influencing it. And then a hyperbolic orbit. Those last two are unbound. We can look at exactly what kind of speeds we're talking about. So if we look at the amount of velocity that is required to put something into a circular orbit, or essentially have something fall without hitting the Earth ever, you can see that it is. You can play around with the math, and if you're curious, please put in the comments, and I will make a video, actually a short video, actually doing the algebra for you to make this clear. You can see it where you have velocity equals, or the circular orbit equals the square root of g over m. And thank you, Judy, for asking that question. I will answer that in a moment. So that is the speed that is required for a circular orbit. And you can put in the numbers, the gravitational constant, the mass of the Earth, and then divided by the radius of the Earth, square it, and that's how fast you need to go in order to go into a circular orbit. And that's how fast you need to go tangentially to the Earth in order to orbit around the Earth. If you want to escape the Earth, and you can verify my math, like I said, I believe it's 11.7 kilometers per second. It is the square root of 2 times g over m, gm over r, rather. So it is a square root of 2 times larger than the circular velocity. So let's go back to Copernicus, or rather, Kepler's third law. I promised a while ago that I would actually derive Kepler's third law, 3 laws from planetary motion. And I do plan on doing that. So without proof, I'm just going to show you what Kepler's third law actually states without what Kepler's third law actually states if Kepler was able to analyze the data without having to work on ratios. Kepler's the Newtonian revision of Kepler's third law, or the Newtonian version of the harmonic law, is that the period of period of an object squared is equal to the semi-major axis cubed times the quantity 4 pi squared over g times the mass of the system. So if you have the Earth and the Sun, then you can run the numbers, and that m would be the total mass of the Earth plus the mass of the Sun. This is one of the key ways that we can determine the masses of celestial bodies, because now the wonderful thing is, this is no longer a relational quantity. This is no longer just applicable to the solar system. You can apply this baby anywhere you have mass. So, for instance, let's say that I want to know what the mass of Jupiter is. And if you have a telescope and a digital camera, you can do this at home. What you can do is, if you measure basically take pictures of take pictures. I'm getting excited. You take pictures of the Galilean moons over time. You can measure what the period of oscillation is, and you can measure the semi-major axis, how far it goes out. The rest are constants. So you can get 4 pi squared over g is just a constant. You can use that to get the total mass of Jupiter and Io, or Jupiter and whatever moon. But really, because the moons are so much less massive than Jupiter, they're insignificant, they're negligible, you can throw it out. So to first order, you now have the mass of Jupiter. So that's how we weigh things. Well, in a simplistic way, like I said, in a first order way. This is how astronomers determine the weights of things, or the primary way we determine the weights of things. And this is also what we refer to as a dynamical mass. Dark matter was found from looking at galaxies, looking at the mass of galaxies through or calculating the dynamical mass of a galaxy using this law. So, like I said, this is generalized to anything: the Earth going around the sun going around another star, if that were happening, 2 galaxies going around each other. It's amazing how this small equation governs the behavior, or describes the behavior, of just about everything involving gravity in the universe, orbiting around one another. It's fantastic. I love it. All right. So that ends my lecture on gravity and orbits. So I hope you enjoyed it. If you have any questions, feel free to ask me now, or and like I said, if Gary is still around, I am willing to stick around. Those of you who are my students, you can basically sign off, or you can listen to me have a conversation with a flat earther. So if you want it, I will stick around for a little bit and answer any questions anyone has, probably for the next 15 minutes or so, because I have to get on with the rest of my day. I meant to cover this. Man, I really need to update these slide decks. I'll get back to it. I promise. I will get back to it. I will make sure that I have the appropriate slides to illustrate why it appears that the moon orbits around the Earth and not the other way around, or why the Earth appears to revolve around the sun and not the other way around. It has, again, to do with the masses of the bodies involved. Maybe all the cool planets are cloaked. Maybe, but Chris, you're actually kind of on something there. So there is in a very loose way, there are various types of dark matter there around, but you can generalize them basically into 2 camps that have the really unfortunate names of WIMPs and machos. A WIMP is a weakly interacting massive particle. A macho is a massive compact halo object. Now, what does that mean? What does that mean? Well, a WIMP is a particle of matter that has very, 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 very little mass, but it is non-zero. It does have some mass, but not a whole lot. And it only interacts gravitationally with other matter. So if you have this particle and it streams by a proton, then the proton will react to that mass gravitationally, but it will not react to that mass either electrostatically or through a nuclear process or any nuclear process. So it just interacts gravitationally. That's where we get into things like neutrinos. Neutrinos, which we have measured, is a candidate or a suspected candidate or is a candidate for dark matter. We believe that neutrinos might. I won't get into the weeds. There are problems with neutrinos. Basically, we think dark matter should be slow moving, should have very low energy, or cold, whereas neutrinos are the ones that we can see or we've detected are all hot. They're all moving very fast. They have lots of energy. So they're not. Then you get into exotic stuff like axions and stuff like that. Stuff that we haven't actually found yet. But to your point, let's go to the machos. Machos are the people who believe that dark matter is machos contend that really the reason why the dark matter is dark is because of our technology. We simply do not have the detectors sensitive enough to measure the brightness of these objects, like planets. Planets are very cold, so if the planet is very, very far away, the amount of light that it sends out to us that we receive is exceedingly tiny. Exceedingly tiny. It's measurable, assuming we have the technology to do it, but it's very, very tiny. So the argument is that that matter out there, that cold dark matter out there, is essentially just stuff we can't see. Planets, white dwarfs that are cooled off, black holes, basically low energetic dust, dust and gas, stuff like that. The problem is, hey Matt, awesome that you're here. The problem with that is there are experiments that have been done to illustrate that there just isn't enough what we call baryonic or normal matter in the universe for those machos to actually exist. So, but yes, I did want to kind of address that because you kind of touched on kind of an argument for it, is that the dark matter isn't actually dark, like exotic. It's just, we just can't see it. It's there, it's normal. We just can't see it. But unfortunately, like I said, there are experiments out there that basically say that no, based on the abundances from the Big Bang, there's just not enough hydrogen and helium in the universe to have created that much matter. So yeah. Yeah, I can go off on that in a while. So, like I said, I don't know if Gary Wybanga is still here, but if he is, again, as I often say to him, I would really love to have a conversation with you, particularly to parse why you think the ground pushing up on you is the dumbest thing you've ever heard. That's a bold claim, but not. Or if anyone else has a question for me, I said I'll be here for another few minutes, or 10 minutes or so. While that's happening, I'm going to again, for those of you who came late, I am going to be resurrecting the Coffee and Science, and really, it's not going to be the same format as I did before. Because I don't have the guests lined up. But what I want to do with Coffee and Science is not only have it as a guest show, basically bring people, scientists, bring them on, but I also want to address the open questions of astronomy or open questions of science, because I think those are just as fascinating as, ooh, look, JWST just found an asteroid with rings or whatever it found. I think the open questions are really well, I'm getting ahead of myself. The open questions are the questions that are going to lead us to a deeper understanding of the universe. Yes, finding these strange bodies, finding these planets and all that, that's going to shore up our understanding of how the universe works and how we describe it. But it's really the answer to the open questions that we don't know. So I want to use Coffee and Science to really highlight those questions. And obviously, as an astronomer, I'm going to study astronomy or concentrate on astronomy. So on Sunday at 10 a.m. Eastern, or what did I say? 3 p.m. UTC, I am going to, I can do this. I'm going to address something from the Flat Earth community. There has been a question raised, or there has been an accusation. There has been statements made that astronomy may, in fact, have a redshift problem. Now, one of the ways that astronomy determines the distances of things, basically, like why, you may have heard that JWST is finding galaxies that do not conform to the Big Bang Theory. That's rubbish. But one of the reasons why you would think that, potentially think that, is the distances to those galaxies are further than we would have expected. Basically, the galaxies that we see are far more evolved than you would expect at that distance. So there is some question from some of whether or not astronomy has a redshift problem. And so I have gotten my grubby little mitts on apparently 9 arguments or 9 instances where astronomy may have such a problem. And so I'm going to look at them, and I'm going to look at them critically. And I'm going to either say, no, this is actually not a problem. This is why. This might be why why these folks have this misconception and why it's not there. And then, or I will say, no, you know what? That is a legitimate open question. That is a legitimate problem that astronomers need to solve. And I will talk about how astronomy, how the community is going about trying to solve them. The only problem that I am aware of, and it's been a while since I looked into this, was one of the arguments for why dark energy may not be a thing or what have you is when you look at the key observations for why dark energy is needed is the supernovae, the type 1a supernovae at the very, very farthest reaches of our universe. One challenge to those results is that there may be systematic problems with that data because it's really far away. The error bars are pretty large. And 2, could be that our understanding of redshift or how light moves, our understanding of redshifts at such a large distance or such a long time ago may actually be incorrect. That's the only one that I know of. But we'll see whether or not that's one of the 9, and if it is, then I will address it, and we will go on from there. Hopefully, people enjoy it. We'll find that interesting. I'm actually looking forward to it. I particularly am looking forward to this sort of format because I know that there are a lot of open questions that I'm like, have we done anything with that? What is the current state of the community on things like dark energy, on things like dark matter, that sort of thing. So anyway. Well, I guess Gary is either no longer in the chat or he is declining my invitation to have a Discord, as it were. So, all right, folks, I will end this with my normal spiel. If you like this content, if you'd like to see more of it, please like, share, and subscribe. Also, if you would like to help me with the outreach that I'm doing here at George Mason University, please consider becoming a Patreon or one of my Patreons. My Patreon link is in my About page on YouTube. All proceeds go to helping us here, buying new equipment, paying tour guides to go out to elementary schools. I'm excited because on the 24th of this month, I'm going out to an elementary school with our inflatable planetarium, so I get to teach basic. I think they're eighth graders. Is that elementary school? I think they're eighth graders. I get to teach eighth graders about the sky using an inflatable planetarium, and I'm going to be taking some undergraduate tour guides along, and so those tour guides need to get paid. And so any help that you would like to give financially, please consider becoming a patron. Like I said, all proceeds go to. I don't keep any of the money; all of it goes to them. So yeah. With that, I will bid you all adieu and a good day. I was thinking there was something else I wanted to. Nope, that's it. All right. Peace out. Clear skies. Have a good one, everybody.